All right, I'm going to go ahead and start talking. While you're working, if you need to, in terms of getting the browser going. Good afternoon, and thank you for coming. My name is Jim Campbell. I'm a retired physician at the University of Nebraska. I've been working with SNOMED a long time, and I am now a data mart manager for our research department at Nebraska, where I am applying some of the skills I've had over many years with SNOMED to the creation of an interoperable data resource for Nebraska medicine. My co-conspirators here today, Stan Huff is there on the right. Stan is one of the co-architects of LOINC. Basically has chaired the LOINC committee since time immemorial, and gave us the exciting news that they're going to be publishing a SNOMED extension of LOINC just a little time back, meaning that we're going to be able to get at least LOINC and SNOMED onto a single platform for purposes which I hope to demonstrate to you this afternoon. To Stan's left is Olivier Bodenreider. Olivier you're still the head of the Lister Hill Center, right? Yeah, of the National Library of Medicine. He has taught me everything I know about ontologies. And he also, and his colleague, Robert Wynn, who, oh, there's Rob, have created an OWL rendition of RX norm, which we have basically imported into our SNOMED extension, as we'll explain later on. Our fourth co-conspirator is Scott Campbell. He's head of pathology informatics at Nebraska Medicine, and I'm sure he'll be here in a little bit. And today, we're basically going to look at a unified ontology for U.S. healthcare and its effect on interoperation. We're going to do a brief introduction to what interoperation is all about. I'm going to talk about some examples and clinical findings on the problem list. Olivier is going to talk about RX norm. Stan is going to talk about LOINC and observables. And the SNOMED and Scott is going to address recent new content in SNOMED that has just been published within the last year for anatomic pathology in cancer. So I want to thank Robert and Olivier for all of the work they've done to create the OWL rendition, which we're going to be showing you in SNOMED today. Back in Nebraska, we tragically lost a colleague this year who was actually the first to work with Rob in terms of pulling the RX norm data into SNOMED, Jay Pedersen. And Jay's duties have been taken over by Stefan Frisima, who is now our programmer in charge of these development activities. I want to thank B2I for all the work they've done with us and creating these various modules for our extension. I want to thank Rory and the tooling team and Kai Cooley for all their help in terms of getting our platform up that we can use today, as well as answering countless questions on my part. And I think we should recognize that in the SNOMED community, the substances group, Tony Morrison, Julie James, and others were instrumental in implementing the international drug model, which Olivier is going to talk to you about, and also all the hard work of the pathology clinical reference group in developing the material that Scott will share with you later. So if you didn't see it before, all of the handouts, which are primarily reference material that I think you should have. Maybe you already have them. If so, you don't need to worry about it. But I'll explain as we go along in terms of what the significance of these various documents are. And then down at the bottom, the platform we're going to be using today is devnebraskabrowser.ihtsdotools.org. I would just mention that, oh, it somehow got blown away. Through the rest of the year, we have this same extension up at our own website on a Snowstorm browser at Nebraska, which is available all the time. Now, Rory's team was good enough to stand up this instance of the Snowstorm, and he will keep it live for a month from today, okay? Because we're going to be using this for a workshop at AMIA as well. Why do we care about interoperability? You know, if you look at any textbook, semantic interoperability is the ability for computers to exchange information and to use it. I think that the ONC this morning said it very well, you know, without any folderol, without any assistance, so that basically the computers can process and use the information meaningfully. It's important for us in healthcare, I think, because of the fact that we are trying to move towards a learning health system where the data that we get in our, is put in our electronic health records is reused for a variety of things in terms of scientific research, quality improvement, public health, et cetera. And that's the reason I think that interoperability is critical to us. We have been playing out a lot of those problems at Nebraska, where we've been participating in several major US national research networks, namely PCORNet, Odyssey, N3C, and a number of other projects. But this is the reason that we're having this discussion today, because I think moving forward, it's important that we support this. As I said, in the learning health system that the Institute of Medicine basically pictured, EHR data can be used by the enterprise site to basically improve their own quality of care and their outcomes for their patients. But then that data, if it can be shared with public health and the research community, then large networks of clinical what we call pragmatic clinical research can develop and thrive. And that's one of the examples I'm going to discuss with you today. Now, interoperation from a technical standpoint, from the computer scientist, is most often modeled as binding of a top-level ontology or information model in some parlance to a set of vocabulary models that serve the various domains that are needed within the electronic health record. That bound to a data representation model and with an interface model that allows clinicians and healthcare givers to actually speak to the computer, if you will, and structure and enter their data. Those are the basic elements of an interoperable system. Now, in the US, as you found out this morning, our Office of National Coordinator is basically leading the efforts towards interoperability. And as far as a top-level ontology is concerned, in the handout material, you will find a copy of US CDI, the US Core Data for Interoperability. This is a category, is a listing of the major classes of information at the top level of the EHR design that the ONC is proposing for interoperation purposes. And in that document, if you take a look at, for example, the problem list, you'll see there's further specification of the appropriate domain ontologies, that is terminologies, which hopefully have enough relationships and so forth to add value as to meaning. Basically should be bound, okay? And we'll talk about what that means concretely for a couple of examples here in a minute. But in general, in the US, the three major ontologies that are in active use and are specified by the ONC for use in interoperable data management are SNOMED, LOINC, and RxNorm. And our current state is that those three terminologies are all published by different organizations. You know, there really hasn't been much interaction until Stan and Regenstrief basically announced that, well, we're going to share the concept model that we've agreed upon with SNOMED and basically show a picture, if you will, an extension of LOINC content actually in native SNOMED CT browser, as we'll see. Those three ontologies, accompanied by the HIPAA transaction code sets, are the standard codes from ONC for US interoperability. Now, the reason for this workshop today is we believe that if we have an ontologic integration and collaboration of our major terminologies, our major domain ontologies, that we have an environment which supports analytics and decision support and related issues much better. And we're going to talk about some examples of that. So you should have brought up the instance of the browser, all right? And I only want to point out at this point that the implementation of LOINC in this particular extension, for example, what's the code for blood glucose in LOINC? Well, there's a bunch. Well, there's a bunch of them, but the most common is this guy, all right? And we have structured the way we've implemented it so that you can search on the key phrases of LOINC or RxNorm, and you will get, you know, those relevant subsections, if you will, of that from that terminology. We changed the fully specified name to clearly indicate that the intellectual property of this is Regenstrief, is LOINC, okay? And similarly with RxNorm, okay, in this example of an augmentin clinical drug, a betamethasone topical cream, okay? You'll see that the fully specified name basically has the RxNorm code. It also has the RxNorm TTY. So you can tell that this concept is a semantic clinical drug in the RxNorm semantic network, okay? And I just wanted to be sure that you understood that what we have implemented here is not yet the LOINC extension, okay? And this is a pilot that we created a couple, 3 years back of about 24,000 LOINC codes. And we will be replacing this in our extension with Stan's work when that is published. But we actually use this in terminology management back in Nebraska. So what you'll find in that browser space then is LOINC, RxNorm, The pathology work that Scott will be talking to you about a little bit later is mostly in the international release right now. So of course that's there. And then we have some developmental content as well, but not much because most of it has been promoted to the international release. And then we've got some clinical extension as well. That's what's in that browser space, okay? And I think I should mention that Olivier and Rob were good enough to, provide us with their OWL version of RxNorm, and that's how we populated the medicinal products, which he will be demonstrating to you. The other thing I want to mention is the machine readable concept model. Okay, we're going to be discussing today the concept model of 3 domains of SNOMED CT: clinical findings, medicinal products, and observable entities. Okay, and the machine readable concept model is basically an executable set of constraints on the use of relationships in SNOMED to build a logical, consistent definition with the way the model is supposed to be displayed. We found out years ago when SNOMED first came out that, if you allowed cutting and pasting of terms together in a haphazard fashion, you get a mess, all right? And the machine readable concept model, okay, where here I've gone to the clinical findings section, all right, over here on the right. And then the machine readable concept model is listed for each and every SNOMED hierarchy. So here, for example, you see that in the clinical findings domain, all right, associated morphology, all right, that second attribute can only be populated by morphologically abnormal structures. That's something that Scott really learned in spades when they were developing all the synoptic coding, because there's a lot of use of that particular attribute there. But I just want you to understand that when you get to the point where you're starting to do work and browsing in SNOMED with the concept model as your guide, and or you're creating new content for your own organization, all right? This is basically the roadmap for how you can legally, or I should say, in an editorial consistent fashion with SNOMED, basically author post-coordinated material. All of the attributes that are available for modeling are listed with each domain, okay? And the value sets on the right indicate what are the proper targets. So for example, if you use associated morphology, you can use things like adenocarcinoma body structure or morphologically abnormal concept. That is legal. And the reason that it's a machine readable concept model is that Kai and Rory's team basically use it in the snowstorm environment so that they can validate any post-coordinated queries that you develop. And it's important that you know about this. I'm sure many of you don't understand all of it now, but this is an important reference thing that we're going to come back to, okay? And this is just a little elaboration about what the machine readable concept model is. And by the way, at the end of the session, we will push copies of all of the presentations up to the handout site, so you can grab them if you wish. All right. So don't worry about details on your notes. In the course of this afternoon, I mean, interoperability plays out in slightly different flavors, if you will, computationally, depending upon the data sets that are being managed and the organizations and their information processing needs. And we're going to discuss two primary examples today in clinical decision support and in clinical data research. And I want to start talking about the interoperation of research data because that's what led me to be interested in the notion of computable phenotypes, which Rachel Richardson wrote a paper about several years ago, and which always consisted, botheringly, of developing these big laundry lists of value sets, which I'll explain in a second. And I wanted to make them truly computable. We're going to discuss a real life a project that we were involved in, okay, within the last 5 years, called the Adaptable Trial, which was a randomized intervention trial of outcomes with 2 doses of aspirin, okay? And I would say parenthetically that that's the first time I got my name in the New England Journal of Medicine, I'll have you know. So I'm sort of proud of it. But the Adaptable Project was a big undertaking. As a pragmatic trial, it was designed such that the research network, this was done with the PicoreNet infrastructure, okay? That the research network would basically do computable phenotypic queries, okay, of the electronic health record, identify patients who were eligible for studies so that they could be approached and asked, and informed consent could be obtained. And then after the intervention of randomization to a dose of aspirin, we were going to follow those patients for 5 years via their electronic health record, looking for the outcomes. Okay, oops. And the outcomes, the endpoints were basically all-cause mortality, myocardial infarctions, and non-fatal stroke. So for 5 years, actually a little longer than that, we were querying their records with a computable phenotype, okay, which is basically a query on a data source, such as an electronic health record, to define the individuals in the data set that fulfill a set of criteria. All right. For example, they have arteriosclerotic coronary vascular disease. That was the primary inclusion criteria. And the computable phenotype that we put together to identify our recruitable population included all of these features, in terms of inclusion, exclusion criteria. So it's pretty complicated query when you come right down to it. It had maybe 8 or 10 moving parts. But all of it rests upon the notion that, as we move into the learning health system, pragmatic research basically hinges upon the ability to reuse the electronic health record data to solve scientific questions, okay? And that's what we're all about today. Now, something that I emphasize with my students back at Nebraska when they're designing their computable phenotypes is you got to pay attention to the semantics, okay? Because, the people who run these studies never bother to actually give you specific definitions of, okay, what is arteriosclerotic coronary vascular disease? You have to basically figure that out and then figure what components of electronic health record data may be available for you to identify that, and then to query the proper, of course, in the electronic record, it's all a set of codes in the end, for the database. Well, following the semantic analysis that I was talking about, in this particular case, patient with arteriosclerotic coronary vascular disease. In clinical medicine, that's a diagnosis or a problem. Okay. That's where we'll find that data in the record if that patient has had arteriosclerotic disease, coronary disease. And so we pull up the US CDI and we find what problems, the problems class. And then we chase it down as to what domain ontologies, and in this case, it's clinical findings, events, and situations with explicit context are relevant from SNOMED for the problem list. Okay, that's the semantic analysis, which allows us to start putting together the query that we're basically looking for. Because in the PCORNet model, the condition table is the table having the top level information of problem list, okay? And so we need to write a query that goes in and pulls out all the codes that correspond to arteriosclerotic ASVD, all right? Now, if you go ahead and browse and look that up, I think you'll satisfy yourself pretty quickly that there's not a clean match, all right? So this is not part of pre-coordinated SNOMED CT. Well, does that mean you can't use SNOMED CT? No, because if you look further, there's lots of examples in there, speaking as a clinician now, of patients who have an arteriosclerotic ASVD diagnosis. So how do we figure that out for our computable phenotype? Okay, here's where we get started with expression constraint language. And we will work this example through together if you'd like to come along, okay? So the diagnosis of ASVD, all right, is in the clinical findings hierarchy in SNOMED. And that may not be obvious to all of you, but just trust me for now, okay? Now, actually, it's a little bit more specific since it's ASV disease. We're actually going to do, let's clear this out. So first of all, ECL basically starts with a focus concept, all right, and then allows you to add refinements, which basically take elements of the concept model, all right, that's appropriate for that domain, for that hierarchy, and then have you populate it with the specifications for what it is you're trying to define. In this case, ASVD. So first of all, we want to go ahead and pull up disease. And it's usually a little faster if I type it this way. Another thing, if you get frustrated, in the handout material, there is all the ECL that we're going to be using for the exercises. And if you downloaded the handout material, you can, well, I'll show you after we're done how you can easily cut and paste it into the window and bang, you're live. And it would also give us this code, which is always a pain in the neck to look up. Actually, I'm going to do that anyway. So here's the answer list. If you're worried about making a passing grade, all right. And here's my definition of arteriosclerotic coronary vascular disease. So I'm going to copy that. I'm going to paste it in the window with these for the ECLs. All right. Now, interestingly, if you go to the browser or the builder at this point, then it shows you what you just did. All right, in a little bit more understandable terms. And I want to discuss that because I want you to understand what went into building this decision. All right. So first of all, this is a disease. I think that's obvious from the name. All right, that we're looking for. Secondly, what is it? What else is in the definition? There's no right or wrong answers. I won't come down on you. It's about the coronary artery, right? So in the concept model under clinical findings, you go and look, and the relevant attribute, that's the defining relationship in the SNOMED concept model for diseases, is finding site. All right. And you know, this is sort of a shorthand, the fully specified name plus the concept ID. We use the FSN for readability, but you don't have to have it with ECL. So we're going to look for diseases with a finding site of what? Now, when you go to look up anatomical terms, the anatomy model in SNOMED has a structure, entity, part. In other words, it's may have 3 codes for every particular thing in terms of how you describe it. And when you're looking for a particular, a tissue or a piece of an organ, always add structure when you look up. So you search on coronary artery structure and you'll find that very quickly. All right. So we're building our definition. All right. And now we're looking for diseases of the coronary artery. We could go ahead and search that, and that would contain, presumably, a subset of all those with arteriosclerosis, if there are any. All right. But now we want to make this computable phenotype computable. So we go and look for ourselves, to what we need in order to pull in the second feature in that definition. Arteriosclerotic coronary vascular disease. So it's arteriosclerosis. Now, SNOMED was started actually by pathologists. So it shouldn't be too surprising to you that there's a lot of detail in pathology, as Scott has found out over the course of the past few years. And arteriosclerosis is a morphologic finding. The pathologist looks under the microscope and sees cholesterol and fibrous tissue and so forth in the artery, and they make a conclusion of arteriosclerosis. Anyway, in the concept model for clinical findings, associated morphology allows any morphologically abnormal concept. All right. And we search for arteriosclerosis, and there it is. All right. And it's quite complete. As I said, it was started by pathologists, and that got a lot of early attention editorially. So we did that in the ECL builder. All right. Then when you pop out to the execute window, go ahead and execute. Now, the description logic classifier is basically computing the reference of this particular post-coordinated expression to all other things in SNOMED. All right. And we specified that it has to be diseases. All right. And we specified that it has to have arteriosclerosis. I'm surprised. Huh? Is that it? That is not a complex set of instructions. I'm not sure what's going on here.
Maybe because we all have a price.
Are we all doing it at the same time?
That may be part of the problem.
If you open it up on any lexicon,
Huh?
if you open it up on any lexicon, it's running fine right now. If you want to do that in the demo,
Any lexicon?
yeah, just don't mind.
Refuse my connection.
That was on purpose, Charles.
You beast.
This is the other copy I was talking to you about. Okay. So this is working on the same system. Bingo. That's usually what we experience. Okay. And look at the codes, and remember in the ECL, we use the double less than sign before disease. That means all descendants and self. So we want that diagnosis if it exists in SNOMED in this extension. And all of its descendants, all of its subtypes, okay? If you just need all examples of diabetes mellitus, and you do an ECL of self and descendants of diabetes mellitus, you'll get the list of all of the tree, which is hundreds of concepts, that are examples of diabetes mellitus, all right? But looking at these, coronary artery disease due to type 1 diabetes, due to type 2, angina co-occurring and due to arterial sclerosis, unstable angina, you can see that a terminologist who wasn't trained in clinical medicine would have a hard time coming up with this value set, because each and every one of these is a code that needs to go in that computable phenotype query. All right. But, fortunately, we don't have to enumerate all of those. And there's a bunch of them. Okay. Because our server back home basically has an API that will take the ECL, execute it against SNOMED, pull it back from our terminology server, and give us the value set that we then plug into our query. And that, Rachel, is what I was talking about when I talked about, truly computable phenotypes, where the underlying ontology basically does the work, if you will. All right. So that's an example. And I think it would probably, are you still getting real slow response time?
Mine's fixed.
I'm sorry?
Mine's working now.
Yeah.
Is anyone else?
Okay. All right. Well, let's try another example. Let's look, and this is from adaptable now. Okay. So what we looked at earlier. Let's look for myocardial infarctions. All right. Now, frankly, there's good segregation of disorders and findings and clinical findings. So you don't really need to worry about, specifying disease or finding, even though some of the purists would say you do on it. Okay, so we're looking for a clinical finding of some type, of diagnosis, if you will. All right. And what do you think would define myocardial infarction?
Finding site of the
Finding site of the heart?
structure.
Heart structure. Like that? Okay. All right. Does that have, I mean, we're looking to build sufficient definitions. That is enough, defined well enough to be able to pull out only the appropriate codes from SNOMED. All right. Do you think we're done? You think this is all the definition?
Well, you find it in that if you just ran that query.
It would be in there among a whole lot of other stuff. Yeah. All right. And Scott, what attribute should I be using to look for that?
Associated morphology.
Okay. Associated morphology. Remember, that's our friend from arterial sclerosis. All right. This is the pathologic observation about the tissue.
And Ronald, this is different than an infarct and an infarct. Infarct. Yeah. Just in case you're driving.
How's this? Infarct, morphologic abnormality.
Yeah, well, that's okay. We want to help that.
All right. No kibitzing, guys. All right. So is that sufficient? Finding in the heart and a morphology of infarct. You don't think so? What do you think it needs, Ron?
I think it needs some myocardial.
That's a good point, because actually the heart includes a lot of things, right? Like the valves and so forth. So Ron thinks you're wrong. It shouldn't be heart. It should be just the heart muscle. All right. Good pickup, Ron. Thank you. Myocardium structure. How's that look to you, Ron? Okay. So I would suppose that this is adequate. And we can go ahead and run that. And this is typical of the response time for these simple queries. You know, they rarely take very long for the classifier to return information. And looking at the results, anterior subendocardial myocardial infarction looks good. Acute ST segment elevation myocardial infarction. You can see there's a lot of different types. All right. And
more than before. There were 37 before, 126 now.
We go back and change that to cardiac structure, really?
No, he didn't run that one.
Oh, we didn't run the other one.
Oh,
Okay.
that's myocardial.
yeah,
Okay.
yeah. So I think you're getting the idea. Now I've put together a series of exercises, you know, designed to introduce you to a few of the more important relationships, attributes that are used in defining a lot of common conditions. All right. I won't say it's exhaustive, but you know, there are many things in the computable, in the machine readable MRCM that basically.
Big shot for our online audience a little better.
Okay. These first three basically just use the two attributes that we've already talked about: finding site and associated morphology. Now, I mentioned in passing, for your interest, that I suggest you browse afterwards. Okay. Part of the inclusion exclusion criteria included things like procedures. Did the patient have a coronary artery bypass graft, or was there a coronary angioplasty? Both the clinical findings hierarchy and the procedures hierarchy in SNOMED are editorially pretty sound. By that I mean they've worked through and they've you know, brought the definitions, the computable definitions, up to good shape. There's fewer primitives in SNOMED today than there ever was before. Primitives being the concepts that don't have a computable definition. Okay. So I've got those two examples in there in your handout material that you might want to take a look at in terms of coronary artery bypass grafting, et cetera, because I'm not trying to limit you to clinical findings and in your work. But I am saying that, we just don't have time to discuss all of that today. So let's talk about another use case. This project basically went to recruit patients with colorectal carcinoma. And Scott, what do you think is involved in the definition of colorectal carcinoma? And I'm sorry, this basically uses the same two attributes. I've got some, well, except that it brings in a new wrinkle. So if we look at clinical findings, finding site, colon structure.
Your problem.
Will it?
Yep.
In terms of finding it, you mean?
Finding it, no. Finding what it's supposed to mean, yes.
No, that's where I'm heading.
Okay.
Okay. And we didn't see anything for colorectum, in that list.
There should be. It's a cecum and or colon and or rectum structure.
Oh, is there?
Yeah.
Oh, really?
Yeah, because we had a big fight about where it begins and where it ends. And you know what? I thought it was a big full of poop discussion, but no, it was actually a really good discussion. So
Okay.
it's the large intestine sans the appendix.
Because I was leading up to the use of set operators in the ECL. With set operators, you can basically take two hierarchical segments of SNOMED and either subtract one from the other, or look at the intersection between them, or look at the union of them, with the operators and, or, and minus. And so anywhere in an ECL, you can take, this is the definition of a set between the parentheses here. This is the set of all colon structures, in terms of SNOMED world, all right? And if you want to add something else to that, like colon and small intestine, then you can basically just put an or, and then a statement for the small intestine structure. And that will, and the ECL compiler will basically then compute that larger set, the union of the two, and use that in the query. And that's where I was heading with that other example. I didn't realize I'd been headed off at the pass.
No, so if you were to, until the findings or the disorders are changed, you'll have to do exactly what you're doing. Is you'll have to look at colon, you'll have to look at rectum, and you'd have to look at cecum.
Okay. I don't think we need to get more complicated now, but I did want to let you know that the set operators expand things very nicely. So for example, if you want all diabetics except those with gestational diabetes, you can take self or descendant of diabetes mellitus minus gestational diabetes. And though that segment will be basically taken out of the set. All right. Sorry.
On your clinical question, are you saying it has to be colorectal or someone just say colon cancer? You want those also?
Well, in designing the research study, you have to talk to the researcher and ask them what the hell they need. And then decide what they want in their inclusion criteria, okay? But in this particular case, yes, they wanted both colon and rectum. And historically, they were actually disjoint. Yeah, Ron.
As minus gone, because in the builder, I see and an or, but I don't see minus anymore.
I'm sorry?
I don't see minus in the ECL builder anymore.
I've used it.
Yeah, it's only there if you don't have a refinement, actually.
Oh, only a certain,
If you start with the focus concept, then you can minus.
All right, I've got to get moving because I'm out of time. All right. But some of the other important use cases I want you to explore. And with the handouts, you can basically go in and do these yourself. And I think you should for interest. We had a researcher who wanted to look for alcohol use disorder. Okay. And when you look those types of things up in SNOMED, it turns out that they're modeled as diseases caused by causative agent is the relative attribute, okay? Causative agent of ethanol. And so you can define alcohol use disorder as all disorders that are caused by ethanol, all right? And then streptococcal disease is obviously the same thing, okay? But in that case, we're talking about a bacterium. You go and look at the machine readable concept model, both of those are legitimate, are in the value set for the causative agent, okay? So those are two examples of use of causative agent, which, you know, comes up not infrequently. I'm just trying to acquaint you with those relationships which commonly pop up in clinical research, okay? Similarly, coronavirus disease, all right, is caused by the severe respiratory whatever virus they named it. And then complications. How do you get when you do a query on coronavirus disease, disorders caused by coronavirus, okay? You'll notice that something like long COVID is not there. Why is that? Well, in the SNOMED model, that's basically defined as a complication, all right? And the relevant attributes for complications are after and during, okay? So disorders, causative agent, and these are all in the examples, so you can take a look. Causative agent of the coronavirus, I'm sorry, after a coronavirus disease, okay, will basically pull out what you're interested in for that. And then you basically OR those two together, all right? Complications of eye surgery, if you look at the after and the during are allowing their value sets procedures. So complications of procedures can easily be computed. The last relationship I wanted to mention was pathologic process. Now, things like infections do have a pathologic process definition. When you want to look for things like parasitic infestations, those are actually defined only as a pathologic condition. And so that's a whirlwind tour of those things which I thought were most relevant to your introduction to use of ECL and computable phenotypes. And I'm sorry that we didn't have more time so we could actually work through them, but the handout material allows you to go ahead and set up your own work plan, assuming that you're interested in this. Next, we're going to go go with Olivier, who's going to talk to us about medications.
Questions? Any questions for Jim before we switch?
I guess I'm providing mine.
Oh, right.
The one question. Yeah, right.
The goal, I hope, is to start sharing some of this. If you're looking for this and you've got your criteria for what you're going to do for your research, and you can get your ECL, and you're going to share the ECL with others so that they can use it as, is that some?
My goal in this is to
Mike,
Oh, okay.
Jeez.
Hell no. My goal in this is to convince, one of the coordinators for the National Pragmatic Trials work at NIH, that we need to start thinking about this in computable phenotype definition and publishing libraries of it. Yeah.
Yeah, they need to know.
And I think there's also clinical uses for that as well. When it comes to writing guidelines, for example, okay, who should be cared for with this guideline in terms of criteria. There's lots of.
I mean, the beauty of this is if you have a multi-institution study and you give them this query and they're all using SNOMED, they're all going to use the exact same criteria at that point in time, even.
And that is where interoperability happens.
Yes.
Okay. All right,
Oh, you got another-
Olivier.
got-
Oh, another one?
Well, I had a question on this one. So this, I guess I'm seeing the value of this then, that we can logically define these queries, but then a group would still have to take this to their database and decide if they're looking at the problem list, or I mean, they would take these lists and then implement them in their different data elements and hope that they've got the mapping.
They wouldn't have to implement it differently. The point is, every one of those databases have a slightly different set of diagnoses that fit the criteria. Okay. I mean, clinical parlance, how you describe alcohol use, acute intoxication of alcohol or whatever, differs between clinicians, and therefore the SNOMED, since SNOMED tries to be clinically precise, that's got a lot of ways to save diabetes. And the point of this is getting a truly comprehensive, logically defined set.
Yeah. Oh, I love this piece because it just the way you describe it lets that local variation happen, but you're standardizing, like, this is all the things that we could be talking about.
Yep. And in network research, I mean, that's a big deal because nobody's electronic health record is exactly like the next guy. Olivier.
thank you, Jim. Good afternoon. I'm Olivier Bodenreider, and this is going to be tag team with my colleague, Rob Wynn. We're both from the National Library of Medicine in the US. And Rob is actually giving a presentation in a concurrent session about something that's relevant to that. So I'm going to say, well, first of all, I want to thank Jim because I'm going to say most of what he said already, but with a drug flavor. So I'm going to say the same thing. I'm going to say attributes are important. You need to pay attention to them. You need to pay attention to the set operators, as he said, and you need to pay attention to the model, to the way the data were put together in the first place in SNOMED. And that's the reason why I'm gonna start by presenting the concept model for medications in SNOMED. In addition to this, there's gonna be one layer, which is that we're gonna talk about interoperability, not just between two institutions running the same query or trying to run the same query, but we're also gonna talk about interoperability between two different ontologies or terminologies. In this case, we're gonna look at the drugs in SNOMED, and at the same time, we want to retrieve from the same query, we want to retrieve the equivalent drugs in the drug model in our XNORM and how we first had to align these two drug models so that we could translate the drugs described in our XNORM into the SNOMED formalism or into the SNOMED model so that we could query both the SNOMED and the RxNorm medications with the same set of queries. What I'm going to show you is experimental. As Jim mentioned, the translation, if you wish, of RxNorm into the SNOMED model is experimental for now. And you're going to be able to see a preview of it. So let's start by looking at drugs in SNOMED. I'm referring to an old presentation that I made a while ago. This was work done by Julie James, who is one of the authors of the SNOMED model. And this is a relatively old paper, but you can read it, and it's going to give you much more background than I will be able to present today. So it's still valid. It might be 5 years old, but it's still valid. So the question is, this is a drug that you can buy in the US. This is actually the box, a picture of the box. So it's amlodipine bisylate and atorvastatin calcium in tablets of 10 milligram of amlodipine and 10 milligram of atorvastatin. So that seems simple, but there's actually a lot of information in there that we need to be able to represent if we want to be able to do prescription to prescribe this drug and retrieval for clinical analytics. Essentially, what I want you to get from this is that there's essentially, simplifying a little bit, there's essentially 3 important elements to define a clinical drug. One is the ingredient or the substance that goes into it. So amlodipine, atorvastatin. The strength. So 10 milligram of amlodipine, 10 milligram of atorvastatin, that's what we were talking about. But in fact, it is a little bit more complicated than this. And the dose form, we're talking about all tablets in this particular case. So these 3 things, the ingredient or ingredients, the strength, and the dose form are the 3 major elements that define a clinical product. SNOMED also offers information, SNOMED and many other classification systems offer information about drug classes, and this is represented here, and we're going to use this in our queries. However, the drug model, the medicinal product model in the international release of SNOMED CT ignores completely on purpose, ignores notions of packaging and ignores notion of brand, okay? This is left for extension, national extensions, because usually, you know, drugs have slightly different names based on the country, and in some countries they are sold mostly in bulk, and it's for the pharmacist to count the pills and put them in small bottles. That's what happened in the US, whereas in other countries they are already pre-packaged and under blister of 10 or 20 or whatever. So that's why this is not part of the international release. It's left for extension, but the international release provides the foundation for creating these extensions. So if you already know that there's a clinical drug with 10 milligram of atorvastatin and 10 milligram of amlodipine in all tablets, it's easy to stick brand information to this. It's easy to stick packaging information to this. Easy being relatively speaking. I'm going to skip this in the interest of time. Some of these slides are actually for reference purposes, and you will have the slides as part of the handouts. So now, once we've defined the basic, the definitional criteria, the definitional features of the various elements, in your mind, it should immediately be translated into, okay, so there's going to be an attribute for each definitional feature. And that's how we'll be able to, first of all, provide definitions for these products, but also retrieve them by by querying these attributes and the corresponding values. So there's different levels of aggregation that have been created by SNOMED. So the lowest level is the level that combines the ingredient with the strength and the dose form, the three pieces together. And in this case, we need to specify the precise ingredient. I'm not going to get into the details, but remember that we need to specify the precise ingredient there. And the rest of the things are kind of groupers to support navigation in this sea of products, because we're talking about tens of thousands of products. So the clinical drugs in this case. So if you associate an ingredient and a dose form, you have the medicinal product form. If you associate the ingredient alone, if you take the ingredient alone, you have a grouper that allows you to find all the clinical drugs that contain atorvastatin, for example. That's relatively easy. There's a notion of this that's a little bit refined, which involves only. So are we talking about, there are pills of pure atorvastatin, if you wish, and there are pills that associate atorvastatin with amlodipine. For convenience, essentially, you get two drugs in the same pill, and that's easier to swallow, literally. So, so the only piece is important because it allows you to define the products and the groupers fairly precisely. Am I talking about just this ingredient in the pill, or can there be something else? And I should say that the clinical drug ingredient, dose, form, and strength, by definition, is restricted to only. When we prescribe a drug, we want to know exactly what's in the drug, and we need to know if it's atorvastatin alone or atorvastatin in combination with something else, in which case the something else needs to be specified. Okay, so that's what it looks like diagrammatically. At the bottom, there's the clinical drug, and again, it's with the precise ingredient. And the levels above it are groupers. Medicinal product form is the ingredient and the dose form, and the medicinal product alone is just the ingredient. So you can imagine that we're kind of peeling the onion. And so we have three criteria to define the clinical drug, only two to define the medicinal product, and a single one, which is the ingredient when we get to the level of the medicinal product. Jim.
Just a quick comment. In the US domains, electronic health record, the appropriate code set for medication orders should be clinical drugs, because it contains the order should contain clinical drugs, basically.
For the reasons that I mentioned, because you want to know exactly if it's this substance or this substance plus something else, and you need to know in which dose form and at which strength.
And it ends up in the electronic health record in the med orders. Okay, so this is the same thing, but with an example. And the example is simply the very product that we started with, which contains 10 milligrams of amlodipine and 10 milligrams of atorvastatin. And in this case, what you can see at the clinical drug level is that we also specify what the active ingredient is.
Again, there's a lot of information here. There won't be a quiz at the end, but if you're interested in this, that's something that you need to invest a little bit of time in studying, if you wish, before you are completely fluent in the drug model. So what's important here is that there are actually patterns for these various types of entities. And so there's a couple of things that can be specified here. The notion of presentation strength as opposed to a normalized strength. And this involves the notion of a numerator and a denominator, each one having a value and a unit. So we're going to say 10 milligram value and unit in one pill. And that's going to be the denominator, one each. That's going to be the denominator in this case. It's for tablets, but if we're talking about liquids, for example, it's going to be in milligrams per milliliters or things like this. So I kind of glossed over the ingredient, the precise ingredient. And there's one notion that's important, which is the basis of strength substance, which is the substance in reference to which strength is defined. So for example, when we say atorvastatin 10 milligram, it means that the pill has the potency of 10 milligrams of atorvastatin, even if the ingredient in the pill ends up being atorvastatin calcium. So when you say atorvastatin calcium, calcium has its own weight. So it's going to be more than 10 milligram of atorvastatin calcium. But strength in this particular case is expressed in reference to atorvastatin without the calcium. And that's what's referred to as the basis of strength substance, or BOS for short. And the last point is to mention that those forms and units of presentations have been, in SNOMED, have been harmonized with international standards, in particular EDQM, which is an European standard. And this is a long way of explaining that, again, when we say atorvastatin 10 milligram oral tablet and with amlodipine 10 milligram in an oral tablet, we need to say, and there's not going to be anything else than these two. Because if you use this as a query, or if you don't specify the closure, there might be a third drug in the same pill. And there might be such pills that have more than these two drugs combined together with these milligrams, with this particular strength. So it's really important that to define the clinical product, there be a way of saying, and there's nothing else there. And depending on how you express this and which formalism you express this, there are different ways of expressing the closure. And the way that SNOMED settled for is actually counting the number of active ingredients. So in this case, we're going to say there's atorvastatin, there's amlodipine, and there's only 2 active ingredients, which means that there's no room for a third one. So it's kind of peculiar to say it in this way, but it works, and that's why it was used in SNOMED. So when we look at the description logics representation, it looks like this. That's kind of ugly and scary. So especially if you haven't, seen it before, but it's essentially the same thing as the ECL. It's kind of like the same thing as the ECL. What you can see here is that at the top, that we're talking about a medicinal product. That's the focus concept, pretty much. And then there's a bunch of refinements that we add to this to say exactly everything that we need to say to define this particular clinical drug. And there's a bunch of restrictions or constraints, and that's why the ECL is the expression constraint language, because it allows you to express constraints that restrict the focus concept to get to exactly and only where you need to go. And in this case, these constraints, not surprisingly, involve the manufacturer dose form. I told you that dose form was important. They include the strength, which is expressed as a numerator and a unit, and a denominator and a unit, and also active ingredients. So, and not to forget, at the very end, the count of base of active ingredients, which is atorvastatin, amlodipine, and nothing else, only 2 of them, okay? So that's all what's expressed in there. Makes it for an interesting query when you have to write the ECL query for it, but it's all doable as long as you know what the model is about, as long as you know these attributes and the sets of values that can be used. I also need to talk briefly about drug classes, because to some extent, that's the interesting stuff. The drugs are cool, but if we know what the drugs are used for, what they can be used for, or what they do in practice, that's even more interesting sometimes. And that's important also for searching purposes. So there's essentially 3 main types of groupers. One I will take out of the discussion immediately is based on the site of administration, because it's relatively trivial. But based on disposition, which is essentially what's the mechanism of action of the drug, and atorvastatin is HMJ-CoA reductase inhibitor, which means statin in plain language. Other groupers refer to the chemical structure. And the last type of groupers refer to the therapeutic role. What is the drug used for? It's a proxy for what the therapeutic role is. And it's not fully populated in SNOMED International, because there's a regulatory aspect for what indications a drug can be used in a given country, for example. So a lot of the therapeutic roles are actually left for the national extensions to populate. So we're going to see some of these examples. So it becomes interesting when you put all this together and you show the relationships. You get a diagram like this. And again, we're not going to study it too much, but you can see that all comes together fairly nicely. And we have different levels of aggregation that we can use to navigate the drug realm, or the realm of clinical drugs, with the various levels of aggregations that I mentioned already, based on an ingredient, that's the medicinal product, based on an ingredient and a strength, that the medicinal form, based on the various classes, and that's the groupers that are color-coded here. And again, this allows you to get a full and relatively nice picture, if complicated, but relatively nice picture of the hierarchy of medicinal products in SNOMED. This is the equivalent to the owl that we saw before, but rendered with the diagrams that we're used to in SNOMED, but that contains exactly the same information, just with a different formalism for presentation, just different notation. I'm going to skip this. It just says that actually the new concept model that SNOMED created was much better than the previous one that wasn't much of a model in the first place. And that's the reason why there was a lot of effort put in by SNOMED International back 5 years ago. It was a multi-year effort to actually rework this concept model. Okay, so now that you know everything about the SNOMED model for medications, we're going to take a look at the same thing, but in RxNorm, because again, what we're after is interoperability, and we need to understand these two models so we can align them and transform one into the other and query them both together. Everybody's okay? Good. So I'm going to do a simple version of this. And again, this is a paper that was published a few years ago. If you want more detail about this, everything that you need to know is going to be in the paper, and it's publicly available. So this is essentially what this is a recap of what we just said about the SNOMED CT entities for medicinal products, all the way to clinical drugs. And this is essentially the equivalent entities in RxNorm. And as you can see here, it's not too bad. They align pretty well. So the clinical drug has the semantic clinical drug or SCD clinical drug in RxNorm. The medicinal product form has an equivalent, which is the clinical drug form. There's already something that you can see here is that the clinical drug form in RxNorm doesn't specify only. It's left, as context for the user to image it. Or it's implied depending on the context, which means that a clinical drug form in RxNorm can be translated either to a medicinal product form or a medicinal product form only. And in fact, when we do the conversion, we should translate it into two different things. Because again, RxNorm doesn't distinguish between the two. It knows that the two exist, but doesn't distinguish between the two. And that's even more true of the top level, which is the ingredient or the precise ingredient, which is equivalent to the medicinal product, but that's also equivalent to the substance. So SNOMED distinguishes between the aspirin product and aspirin the product and aspirin the substance, in the sense that aspirin the product is just a product that contains aspirin the substance as its substance. So in the RxNorm world, the creators of RxNorm decided that, everybody knows that there's a product and the substance, and everybody knows that they are different. It just depends on the context that you refer to one or the other. So let's just smoosh them together. That's the technical term that they use to not make the difference, if you wish. But again, you need to be aware of the difference when you want to translate RxNorm into SNOMED, because you know that when you see aspirin, you're going to need to have two versions of it in SNOMED, aspirin the substance and aspirin the product, and depending on the context, you will need to translate in two different things. However, other than this, things are fairly reasonably aligned, so that it's not unreasonable to think that we can take RxNorm medications and translate them into the SNOMED model, with the few caveats that I mentioned that we need to pay attention to. That's essentially what this paper was trying to say, and I'm not going to go into much more of this. So there's more similarities than differences between the two models, and the differences that exist are not such that you cannot reconcile them, you cannot take them into account if you want to do translation. And so with this, with this taken care of, what we thought is that we could actually do the translation. And that's what I've done with my co-author, co-presenter, Rob Wynn, who just came out of the other session, because it would have been nice if you had the possibility to listen to his presentation half an hour ago, because it was essentially an account for how we did it and what we learned doing it. So what we did, or what Rob did, because I just do the hand waving and he does the hard work. What he did is we created logical definitions for all clinical drugs in RxNorm, and we described them with the SNOMED model that I presented earlier, doing the kind of, using the assumptions that I've presented. And so once we've done this, we have the original RxNorm, the RxNorm translated into SNOMED and in OWL, and we have the OWL file for SNOMED itself, SNOMED, the international release. We take the two OWL files, and now we can run them through a classifier. And what the classifier is going to do is find when two classes are equivalent. And we're interested in the equivalences between an RxNorm class for a medication and a SNOMED class for a medication. And they don't need to be exactly the same, but they need to be equivalent for the classifier to find them equivalent. And so we inferred logical equivalences. And since RxNorm already integrates SNOMED, or provides, asserts equivalences to SNOMED, it was interesting for us to compare the inferences that we were able to make to the inferences that had been made by experts. And when the experts made inferences that we couldn't make, it is because our process doesn't work completely well, or because there are errors somewhere in the data. And that's the kind of things that we've been exploring, and that Rob was reporting on in his presentation. So if you're interested, there's some information in the presentation that he just gave. Any questions so far? Have I lost you for good? Yes.
Yeah.
So thank you for your presentation. It's a really comprehensive view of medications. I'm representing Oracle. In our EHRs, we have, I was wondering, how do you handle more complex examples, such as volume-based medications? And there are differences between concentrations versus strength versus dose. And we typically have some custom solutions to it. And I was looking for seeing you maybe presenting to us what would be the most, the right way of aligning such medications.
Okay, so 15
minutes to the break.
15 minutes to the break. So that's my answer to you. No, just kidding. So I think your question is, so when we do these kind of comparisons between SNOMED and RxNorm, there are differences. So we are able to automatically translate or convert, what is it, 85%, Rob?
76.
76, close enough. Yeah, so three-thirds we can convert fairly easily, and the rest, there are difficulties. And one of the difficulties is how to pick the right template. So are we talking about presentation strength or concentration strength? Are we talking about normalized concentrations for some injectables versus presentation strength? Yeah, so that's the 25% that remain to be looked at. So I'm afraid I don't have a magic bullet for you to say how to do it. It's a bunch of people that need to look at the data and see, and SNOMED has changed some at the margin. SNOMED has changed about the templates that are used for injectables over time. So yeah, no easy solution, no free lunch here.
Because these medications may cause patient safety in many cases. That's why I would assume that you will look at these issues sooner than later.
Well,
so then the next
no,
question.
So I understand. So all this is important and shouldn't be taken trivially. I told you that this conversion that we've made is experimental, which means that it shouldn't be, even if the 75% we're pretty confident that they're good, and some of the rest is good also, it shouldn't be, distributed like this without further review and without ironing out some of these differences.
Right. I guess my question is how to get involved to make sure that you are also addressing our needs. And I was wondering, what is your opinion on inactive ingredients? Because they could be allergens to some of the patients. And there is no standard on inclusion, exclusion, and operational workflows in the EHRs.
So that's an easy one. Inactive ingredients are not part of the SNOMED model or the RxNOM models, so we don't talk about them. Not saying they are not important to some people. They are certainly listed in the structured product labeling information, and as they should. It's just something that's out of scope for the models that I've talked about.
I'm guessing you're planning to include them at some point, right?
Don't put more words in my mouth than there's room for.
And I guess my last question, but it may be to your colleague more than you. And the question is, your colleague just mentioned that, well, the orderable should contain the drug, the form potentially, right? The route. However, in order to operate with the processes inside of EHRs, we implementing large drug vocabularies such as FDB, right? And the question is that you can also agree with me that the granularity of the orderable versus the granularity of these driving workflow forces different. So you may have one clinical drug and 5 FDB equivalents associated with this, right?
Good for them.
So wait. So wait.
I think I'm sorry. I'm happy to take your question offline if you wish to continue the conversation. I don't want to cut you short, but I think it's going to take us way beyond what I intended to talk about and way beyond what's represented there. So it's somewhat irrelevant, with no offense to you in the first place. It's irrelevant to the workshop and to the scope of what we promised to show today. Okay, but happy to take this further with you at the break. Okay, so now the fun part, which is where we have audience participation. I have, I believe, 7 queries or something like this, and there are some differences for some of these queries between this and the handouts. We'll fix this tonight, and we'll put the final set of queries.
Can I make a comment?
Sure, go ahead.
And
with the mic.
And relative to the
Microphone.
relative to my session, there are lots of examples that we've run across this year of was the patient treated with a systemic antibiotic? All right. So in computable phenotypes and identifying populations, that's where we're coming from.
So I think in the interest of time, we're gonna essentially do cut and paste between this. I'm not going to try and build, painstakingly all the queries. It can be done. They've all been, tested, but I think we need to. I would like to show you the intent behind these queries more than the results, if you wish. Okay, so the first one, and these queries were actually created mostly by Jim Campbell. Thank you. So
Mostly from experience with.
yeah, absolutely. From experience and from your clinical experience, so that they are valid queries, if you wish. So we're looking first at antibacterial clinical drugs available for all use. So what are the important attributes that we need to focus on if we want to query this? Well, first of all, the type of things that we're looking for is a medicinal product. It's in the medicinal product hierarchy. That's one thing. We obviously we want to focus on the oral medications. That's the oral use here. And so we know that this is going to be translated into a dose form kind of attribute. And the dose form for this, if you look at the machine readable concept model, as Jim asked us to do, we would find that what's used to specify the dose form has manufactured dose form. And then there's the antibacterial part. Well, the antibacterial is actually the role that the drug plays, and the formal way to formalize therapeutic role is plays role. So what we're going to say is we're looking for a medicinal product. That's the first part. That's the focus. And then we're going to refine the focus with two things. We want this medicinal product to play the role of an antibacterial, and the way we specify this is with antibacterial therapeutic role. And we need a second, so with an and in between, we need a second constraint, which is the dose form. So has manufactured dose form, all dose form. And if we take this, which I won't be able to do unless. Yeah. Okay. And okay, so we're gonna do this for at least one, and so I can, since I have it, I can use the main thing here. Okay, that's where I paste it, and when I execute, I find all my oral antibacterials, pretty much. What I want you to pay attention to is that I find them in different, not only different flavors, but from the many sources, the two sources that have been integrated in our collection of terminologies. Remember that we're querying at the same time SNOMED, the international version of SNOMED, this extension of sorts that we created with our XNorm, and the LOINC extension. And so these three are in the same knowledge base, if you wish. And so the ECLs hit all three. And so for medications, what we're hitting is essentially SNOMED and our XNorm. And remember that we can do this because our XNorm was translated into the SNOMED model. And that's the reason why we can do this here. And so what we see here is that the first elements, didn't mean to click on it. Oops, that's not where I wanted. Okay, so let's do it again. So what I wanted you to pay attention to is that some of these drugs come from our XNorm. That's the first one. It is a branded drug, actually. Whereas if we go down the road, but there's many of them. If we go down the road, some of these will be the SNOMED clinical drugs. Any questions?
I would mention, Olivier, if your goal is to just have the prescribable drug, if your goal is just to get the prescribable drugs, then you can do a filter on the FSN looking for RX norm as a term, and then it'll just pull out the RX norm drugs.
In this particular instance, I mean, if it became an extension, a proper extension, I think we wouldn't be able to do this, but they would actually coalesce because.
I've got an example of that.
Okay. So something slightly different here, but relatively similar. Now we want the antibacterial clinical drugs for systemic administration. So the difference between the previous one is that it was on the oral. Systemic is actually oral or parenteral. And as Jim mentioned in his ECL queries, it's just a matter of putting an OR here on the constraint, on the values for the constraint for manufactured dose form. And we're going to say we want the manufactured dose form to be an oral dose form or a parenteral dose form, and any of the descendants. So again, I'm not going to show it to you, this one, because it's relatively trivial. And I invite you to test all these queries and feel them for yourself if you wish, but there's not too much of a need to go much faster. This one is a variant also. We want the antibacterial for eye drops. So it's just a different manufactured dose form that we're going to put in, and we use the ocular dose form instead of oral or parenteral. So just variants of the same query. But there's a point to my story, because now we want the eye drops for glaucoma. So in this case, well, this is also a variant. And the eye drops for glaucoma are just going to be a variant of the eye drops for the antibacterial eye drops, if you wish. So we switch the value for the therapeutic role. In this case, it's going to be place role anti-glaucoma therapeutic role. Now, this one is more interesting, because it builds upon the previous one, but with a difference. Now, I want to see all drugs that treat glaucoma, not just the ones that you stick in your eye, but there are other drugs, there are oral or parenteral drugs that can be used to treat glaucoma, although it's not, it's not the main cases. So we're going to look at this one because I think it's relatively more interesting. And so how did we build this one? We just removed the constraint on the dose form, because now we want all the drugs that treat glaucoma, not just the eye drops. So that's kind of an easy one, because it's just a matter of removing something rather than adding something. So let's do it. And in this case, we find, of course, a bunch of eye drops, ophthalmic solutions, but we also find drugs that are other than this, and I'm trying to see one here. There's an oral tablet here. Okay, so just to show you that there are ways of refining the queries by adding attributes, but sometimes what you need to do is remove an attribute to get to something more generic. Keep that in mind. Okay. I must be close to being at time.
Yeah, I think you need to make the point though about the concrete demands.
Okay, which is what we get here. So a few years ago, SNOMED introduced concrete domains, which is that instead of having a concept to represent the number 5 or 5 milligram, you can actually use 5 as the number. And that's what's behind the reference to concrete domains. And in this particular query, you can say, okay, I would like pills that contain lisinopril, but I want only those pills that contain at least 5 milligrams of lisinopril. And you can do this by specifying the strength. And the strength, as I mentioned before, is represented with a numerator value and a numerator unit. And that's what is referred to here. We say that the numerator value is greater or equal than 5. And then we say that the strength is, the strength unit is milligram. So that's interesting because we can specify this, and then that's a nice way, if you wish, of you would get the 5 milligrams, the 10 milligrams, etc., etc. Say this again.
Can you get a decimal point? Yes.
Yeah. So it's basically everything that can be treated as a real number, I believe. I think the last one that I would like to show you very briefly is the minus operator that we were referring to earlier. And sometimes we need this. For example, we know that a given patient is allergic to sulfa drugs. So they need to be prescribed. They have some kind of an infection. We want to prescribe them an antibacterial, but we know that they are sulfa antibacterial, and we want to remove that from the picture so that we're not going to hit them with something they might be allergic to. So in this case, we're going to use essentially a restriction on the initial query that we use. So I want, all the clinical drugs, all drugs that are antibacterial. That's where we started. In this case, we're going to say minus, I want to remove from this set the set of drugs that are medicinal products and that have essentially a sulfa substance. And there's a class, a chemical class for that, sulfa substance as their ingredient. So minus medicinal product restricted to has precise ingredient, substance with sulfonamide structure, and anti-mechanism of action. There's a class for this already that's pre-built, if you wish. So in this case, that's relatively easy. So just to show you that in queries that become complex now, you can essentially get to what you want. The only thing is that you need to know enough about the model. You need to know enough about how SNOMED is put together in the first place with the attributes, what kind of ranges, targets there are for these attributes, and a little bit of syntax for the ECL queries. But with that, you're pretty much good to go. So I'm not saying it's easy. I'm saying it's doable, provided that you invest a little bit of time in this.
All right, when we get back, Stan will take us through laboratory and LOIC, okay? And since we're 5 minutes late, see you back here at 35 minutes after lunch.
I'm Stan Huff. I work at Graphite Health and work a lot with LOIC. And actually, a long time ago, I worked a lot with SNOMED. But I'm excited to be here and talk about the really the integration of LOIC into a SNOMED extension, and to talk about why we need it. So lots of other statistics about this, but the one that sort of catches my most attention is that medical error is the third leading cause of death in the US, killing roughly 251,000 people a year. And that's astounding. If you do the math, that means like somewhere around 650 people will die today in the US from preventable medical errors. And so we want to do something about that. And it all relates to what we're talking about today, which is making knowledge computable and making it easy to make inferences and associations and relationships between data that support clinical decision support and clinical use of data. Also, physicians do the right thing about 50% of the time. So there's opportunity to improve. A couple of assumptions that I have about this is that it's not improvement of people. I don't think we can make people smarter or better or more or less error prone easily. And so looking to other things. And my background has been one where we relied heavily on clinical decision support at Intermountain Healthcare. And there were any number of things that were created by Scott Evans and Peter Haug and others at Intermountain that all decreased the cost and improved the quality of health that we were providing. So, I think at least one answer, it's certainly not the total answer to those preventable medical errors, but it's clinical decision support. But at the MedInfo conference in Lyon, there was a session called The History of Clinical Decision Support, a 6-decade retrospective, and Kazimir Kulikowski and Robert Greenis and Ted Shortliff and Don Detmer were there. If they were still living, Homer Warner and Octo Barnett and others would have been there. But it was interesting. They talked about the fact that any number of studies had shown the value of clinical decision support tools. But what they noted was the greatest challenge now wasn't sort of the computing part of that. It was that you couldn't transfer one program that you created at Intermountain to another facility or organization because the data representations were so different. Essentially, you had to reprogram the application to accommodate the differences in the way that data was represented. So one of the things we think we can do is start unifying and in particular in the use of LOINC to make LOINC more computable, easier to integrate into clinical decision support and to establish that capability and functionality. And so there's actually been a long history of cooperation between LOINC and SNOMED going back actually into the into the 1990s, but there was the first official agreement was in 2013, and then a new agreement last year in October of 2022. The first one didn't work well because there was basically a rule that you couldn't make a LOINC, you couldn't make a SNOMED code that represented the same information as what was represented in a SNOMED concept. You could make expressions, but it turned out that using expressions was awkward and there wasn't any uptake of that. So we made a new agreement, and what we agreed is, yeah, we can, what we want to do actually is bring the LOINC terminology into SNOMED, into a SNOMED extension, adhering to the file structures and relationships and all of that sort of stuff that comes with SNOMED, but represent exactly the same content as currently exists in LOINC. And we would, there are details here that I don't think are necessarily important, but the benefits, I think, are clear that we wanted to make the LOINC content available more generally to people who are mostly using SNOMED or, exclusively using SNOMED. And selfishly, from the LOINC perspective, we wanted to get a computable ontological representation of LOINC. And again, what we really want to do then is, and what's the reason for the reason, if you will, we want computable relationships so that we can enable decision support and support the community in advancing clinical decision support. So what we've done in the last year is created a preview release that was available on Monday. And it contains, 24,000 concepts, laboratory LOINC concepts. As Jim pointed out, for purposes of this workshop, we're using one that Jim had generated, not Jim alone, but at Nebraska. You can go and look at what we've created at loincsnomed.org. What I would emphasize, especially to this crowd, is that 24,000 is primarily the simple, easy, quantitative measurements in lab. We're still working on lots of other things. But what's there, we really would like people to look at and tell us about what things you want, how to prioritize things, etc. I don't think I'll talk too much about this other than to say, all of the LOINC content will eventually be in the extension. We're going to have one-to-one mapping or one-to-one representation. A better way to say it is that the same meaning will have both a LOINC code and a SNOMED code. And in a sense, we have a simpler job, an easier job than what Olivier was talking about with RxNorm and SNOMED, because in this case, we're collaborating. So if there are things that don't match or don't cover, we can make adjustments on one side or both sides so that we actually get a uniform representation of the knowledge. Again, we're working first on lab, then we're going to do clinical, then we're going to do other things like document ontology and radiology and survey instruments, etc. Now, one thing that is kind of pertinent for this workshop is that extension that we created, and I think it's similar to what Jim has, is really pretty flat. And we intentionally made a decision and talked about it at some length to say that we weren't going to make grouper codes to sort of classify that hierarchy, because we have ECL that we can use instead. And so instead of me having to traverse a predefined hierarchy that somebody else defined, I can create an ECL statement and I can see the hierarchy and see this assumption in whatever way I want and use it for whatever purpose I have in creating that. So the thing that's happening then, this is a different representation of the machine readable concept model. This is actually, you can go into the there's a machine readable concept model. I misspelled up there. Browser that's available directly off of the SNOMED page. And so you go in and you click on this observable entity, and what you can see are, all of the attributes, if you will, that pertain to defining observables. And so you've got, characterizes, component, direct site, all of these other things. So what we're doing, looking at it from the LOINC perspective, LOINC is, meanings in LOINC are basically pre-coordinated concepts from the more primitive concepts that correspond to components, properties, timing, system, scale, and method. And method is in a different color because methods are not always required. And if I had it to do over again, they wouldn't be there. They would be required to be sent with data, but they wouldn't be pre-coordinated into the meaning of the concept. So, you know, you just look at this, that, you know, body temperature is, if you will, the component. It's a temperature that you're actually measuring at a point in time and orally, and it's a quantitative measurement. So that's the thing. Now, so if you just put it together, and this doesn't show up too good, but I mean, in machine readable concept model, again, you have the observable entity, and then the things that make that up are a component, and it has the same name. That one has the same name in both places. So that particular part is called component in SNOMED. It's called component in LOINC. Property is the same thing. The property is called the same both places. The time part we call, you know, LOINC calls timing. In SNOMED, it's called time aspect. When you're talking about what kind of thing you measured the component in, then it can be in a specimen, and you know, it can be about a body structure. If you're talking about clinical LOINC, it can be about a physical object, all of that kind of stuff. So that in SNOMED is called the direct site, and in LOINC it's called system. Scale, which is, you know, whether this thing is quantitative or a coded item, an ordinal item, that kind of thing is scale. That's called scale type in SNOMED, and it's called scale in LOINC. And then you have technique in SNOMED, and that's called method in LOINC. So that's the way that the major components line up. And this is, like I said, this is tremendously simpler than the medication things that Olivier was talking about. So to jump in then, and I'm actually going to go to one that I did, and the use case for this is, and this is sort of operational and not so glitzy in a sense, but one of the things that's going on practically now is, and these concepts were talked about by Mickey Tripathi this morning, and well known in the United States. You know, we have this catalog of kinds of data that are specified in the US CDI that says what kind of data people need to be able to exchange. And it says things like, and you should use LOINC codes for this, and you should use SNOMED codes for that, all of that sort of stuff. When you start operationalizing that, what happens is that using FHIR as the basis for interactions, a system that needs information poses a query through a FHIR API to another system that has the information they want. And the way they pose that query is that they use a LOINC code to say, you know, I want serum glucoses on this patient. Now, one of the challenges that they're having in practical use of this is you can ask the same question from different systems. You can ask the same question from of people who have the same brand of system, an Epic system or a Cerner Oracle Cerner system, and you get back different kinds of data when you pose the same question. And so we want to try and resolve and work on that. And so, for instance, you could ask for in a query, you could ask for LOINC code 2345-7, which means glucose mass concentration at a point in time in serum or plasma as a quantitative measure. And then the question would be, for instance, okay, and then there are sort of two questions that can come up. One is, okay, if I'm receiving that query, what do I have in my database that might be subsumed by that concept? And the second thing that can happen is, you know, I get the response to my query and I get things back and I look at them and I go, is that really what I asked for? so I can test whether what I got was in fact that thing. So now I also have to confess that I'm probably the least skilled in the use of ECL. But I had a lot of fun playing around. And the way I did this, and I'll come back to this kind of long query here and show how I got there. You know, let's see, let me look just quick here. Yeah. So I have to remember the right name to get started with. So just to get started, clear that one out, go to the ECL builder. Clear that, and then I can say, tour, observe. And so first off, and then I can say, okay, for that guy and actually go ahead and execute him. And I see it, you know, it found 22,638 concepts. So that's pretty much all of the concepts that are in there. And then, so once I know that, for instance, then I can start doing other things I can do at a refinement. And I can say, oh, what I want to do first is, you know, constrained component in that clinical laboratory observable. And of course, these are the names that are in the machine readable concept model. And I can say, okay, let's do something, you know, let's do something simple. Let's just say we want then to find all of these glucose values. And I need to, whoops, I messed up. And, you know, and then I've got glucose as substance and all that sort. So we just choose glucose as substance and say, okay, and let's execute that one. And now I get 122 concepts. Now, depending on what my purpose is, you know, this says, oh, I've got glucoses that are related to test strips. That's mass volume in blood. This one's serum or plasma. But then I've got urine ones in here and a bunch of stuff. And, you know, that original white code we started with was really talking about glucose in serum or plasma. And so I can go back here, go back to the ECL builder and put further refinements on here and say, oh, the direct site that I want to look for is and I actually got some choices here, but I can do blood and there's blood the substance, but then there's also down here, oh, I'm not smart enough. Oh, I'm not smart there. Blood the specimen, which is the one you want. Say, okay. And then I can execute that guy. And now I'm down to 58 concepts. So now these are things that are, you know, blood that glucose that's measured in blood or serum or plasma. But then, oh, there's these things in here with 2 hours, you know, after a meal. There is post-dialysis measurements in here. And normally those things aren't the things that you would be asking for if you ask for that naked, that sort of high level serum glucose code, because those are particular circumstances now that this is, part of a challenge test or something else. So you wouldn't use it for routine management of the patient. You would use it only in the context of what it was created. So, and I found it actually, once I kind of got used to this, it was really kind of fun to say, oh, well, how would you do this? How would you do that? And, it was great to develop it. So coming back to this one though, so what I wanted to, what I did here, and actually used the minus sign and the whole thing here. So this first thing basically defines all of the same things that are part of this definition: glucose mass concentration in serum plasma at a point in time, quantitative measurement. And then for my purposes, I didn't want all of those things that were part of a challenge, or in SNOMED concepts, preconditions that existed before the measurement was made. And so what I did is I took this exact part up here and then I added on to the end of it, the things that had preconditions, said, oh, okay. And I want the things, not only those things, but I want specifically the things that have preconditions. And I'm going to subtract those from the collection of things that have this glucose. So if I take that whole thing and let's see, is this a DOS thing? Control? Yeah.
You can use Control C, or you can right click. Should give you a copy paste.
Copy paste thing too. Okay. And get back over here. And then scroll up here. And paste. So we got the whole statement in there, and I execute it. And now I got 7 concepts. And now it's interesting because the things that are varying now in that collection of concepts are things that are legitimate questions about whether you should return them or not in response to that query. So, this one is being measured by a test strip. This one is in venous blood. This one is in arterial blood. This was in capillary blood. This is in serum or plasma. This is the one that we started with. No, it's a little different. It's blood. And this one's manual test strip. And so you can at least make an explicit decision about what things should be returned from that query. And it will bring to your mind, oh, do I want these things done by test strip, or do I want just the things that were done by an in-laboratory CLIA approved lab result sort of situation? And also the question, is, for my purposes, do I want venous blood and arterial blood, or do I just want serum plasma? What is it that I want? So it exposes to people who are using the data what's available and what might be returned. And so you can see that depending on what I'm doing, I might want to ask a much more specific question when I query through a FHIR API for what I want. And if I'm returning results from the query, I need to be aware of what things might be, if you will, children or grouped with that particular that could be subsumed under that LOIN code that was asked for in the query. So there's that. And there, any number of interesting things that you can do. This is one that Jim wrote that you build this up basically in exactly the same way. You know, if you wanted tests that indicated COVID-19 active disease, at least some of those would be found basically by looking for the component which would be the RNA of the respiratory, of COVID, plus the antigens that are present. Now you could further refine this, for instance, and say, particular antigens or other things, but that gives you 11 concepts back. So another use case, and this is again sort of operational. One of the things that we're trying to do is create a truly standardized representation for clinical data, meaning that we want to have one preferred representation for a given data element. And as I said, one of the challenges that we have is the representation of lab data that has methodologies associated with it. You always want to know the methodology, but if we had our way, our preferred representation would always be, if you will, sort of the pure analyte and its system point in time, that information, and then post-coordinate in the message, the method. Well, what that means, though, we expect that we're going to be getting data from systems that use the pre-coordinated LOINC codes. And so you want to be able to recognize a test that's coming in that is a laboratory test, but has a methodology associated with it, as opposed to being the methodless one. This is not exactly that query, but what this query does, whoops, big mistake, is it finds all of the, and I can use this query as a way of basically using that minus sign. I can find all of the, I can find all of the tests that have one of the methods, but this is the way to find what all of the methods are. And so we take that one over here again. Scroll up here. So it's a fairly simple query. And then, go ahead and execute that one. And then you get a list here, 160 different things that where are all the methods that you can use with laboratory data. So, direct antiglobulin test, dilution, Russell Viper venom, all kinds of things that I don't even know. Clot lysis time technique, etc. So, that's pretty much all I have to say. So,
Stan, if I could just make a comment, can you scroll back to your ECL? This was one thing I didn't discuss earlier that, Stan has demonstrated. Kai explained this dot syntax to me.
So right here.
What this, yes, I mean, you're looking at that set of terms. And what this does is it looks for the values populated in the technique for all the terms in that group. Okay, so it tells you what are all the methods that are actually installed in active lab
in what's already been specified in the rest of the expression. So that's a pretty cool thing too. I've forgotten how special that was. So that's it. So I'll stop there, but I'll be glad to take any questions or okay. Back to whoever's next.
Scott's next.
Scott.
Scott, you've got a new slide set?
No.
Oh, okay. It's just,
We did a 2-slide in set, but. No, you should ask questions. Wait, can I ask Stan a question? Jim wants to show some stuff at the end, so you don't have to take up all the time.
Oh, oh, good.
oh, there it is. I think this one's yours.
Yeah, that's fine. All right. So this one, hi, everybody. I'm Scott Campbell, University of Nebraska, and I have a cold, or the tail end of a cold. So my throat is not always this deep. Usually I'm a falsetto. Keep it short. Why don't you give it, Paul? You could, no, you could do it. Oh, wonderful. You're so nice. The Dutch are so nice. Until they're not. All right, let me do this real quick. Oh, everything's hidden. There we go. All right, so what I thought I'd do today, this is a content area that's brand new to SNOMED, specifically for cancer synoptic reporting and cancer pathology. So some of the things I thought I'd do is basically give you an introduction on some of this. And some people don't even know what the heck pathology and cancer and synoptic reporting really addresses. So I have some great pictures. Apologies if they're before dinner. But anyway, it's all been a product of this group that was the cancer pathology or cancer pathology reporting group project, cancer synoptic working group. Anyway, so I'm briefly going to hit some of the content. There is a much more in-depth session tomorrow about how to implement this and things to consider.
Can you check that chat just to make sure that we're not ignoring a virtual participant?
Nope. Got Q's and A's.
It's fine. That's an old message.
It's an old. Oh, it's Stefan, and he's in bed already. It's another one of those Dutchmen. All right, we could forget him anyway. So
What's wrong with Stefan?
nothing, Ronald. I'm just nothing. Just maybe there is, but I'm just not going to say. Okay. So did I? Oh, all right. Come on now. Here we go. All right. So in general, I really want to talk more about what the content is and how you're going to interrogate it. You've gotten all this ECL discussion here. So gave some fun ECL queries that Jim will be distributing. Well, fun is a relatively, it's a personal term. So you can think they're fun or not. And they're done in scenarios. So just a couple of syntactically in ECL, for those who are pseudocoders, the comment is a slash star and then a star slash to the comments out code. And so the scenarios I gave you build off of each other. And so you can comment things in and out and see how that goes. So when you do that, you might run into an error unless you have apply a comma but you'll figure that out. It'll yell at you. So, but your takeaways today, I really want you to take away that, synoptic structure of pathology reporting. What is it? The data architectures that are really suitable for the synoptic data storage, and then some query use cases using ECL, assuming we get that far. So, all right, the gross stuff. So people want to know, we have one pathologist in the room and a fake one. But basically what happens in terms of cancer pathology and actually anatomic pathology in general is somebody gets a surgery and effectively, they take out something, and whatever that thing is brought, or things are brought down to a room that we call the gross room. And it's gross for not just because of the size, but also because it's kind of gross in the sick kind of way. And at any rate, the surgeon excises tissue, is brought into the gross room, and it could be a pathologist, it could be a pathology associate, or it could be a resident. They assess this tissue and say, well, what is it? Here's what the surgeon said it was. Did the surgeon really know what it was? This is very common. And did they mix lymph nodes together with things that, whatever. But each part is characterized. It's, oh, this is a liver, this is a lymph node, this whatnot. And it's described in terms that convey what the actual physical piece of tissue looked like, whether it looked diseased, healthy, necrotic, whatnot. There's another little thing that goes on in the gross room before we start making tissue blocks. They'll actually quickly cut the tissue, quick frozen. It's like quick frozen food, except it's like quick frozen liver. Cut it, briefly stain it, look at it under a microscope quickly and say it's cancer or it's not, right? Or the margin is clear or it's not. It's a down and dirty diagnosis, but it basically tells, because this is usually happening while the patient's still open in the surgical suite, and they want to know, did they get the tumor? Okay, so this is a really quick thing. And is it, in some cases, is it cancer? If it's cancer or if it's invaded to a certain point, we're stopping, we're closing this patient. There's a lot of emergent, critical decisions that have to be made there. But assuming that, the surgery completes, basically this gross piece of tissue is reviewed, and sections of it are it's really bad, diced. And then, well, it's put in formalin. So when it's put in formalin, it stops the metabolic process in place. Okay, and it sits there for about 12 to 24 hours, depending on the thickness of the tissue. That tissue then is taken to the histology lab, where it is embedded in paraffin through a series of dips. It's all automated now, so it's desiccated. It's, the water's removed. It's replaced with alcohol. Alcohol's removed. It's replaced with wax, and it does all these kind of fun things. So, but basically the tissue's put into these paraffin blocks, and then they're cut, and they're cut into, Stan, what is it? 30 microns? Is that about the thickness of a piece of tissue? I think it's something like that. It's really small. And then they're put onto a glass cover slip, a glass slide cover slip. So something put on top, and then it's sent to a staining line. So it's run through a series of other baths, and it's stained. Typically we use the first and almost always uses hematoxylin eosin, basically stains basic and acid. So dark blue stains acid, or acidic substances look dark blue. So your nucleus turns dark blue, and tissue, parts of the cell outside of that turn pink, and it means something to the pathologist. But basically, after the H&E stain, you see this nice pretty picture. The doctors are looking at that and they say, okay, I see abnormal structures or things that I'm concerned about or not concerned about. They're looking for different architectural components within those pieces of tissue, whether it's, does the cell look normal? Is it look like it's getting angry? Do the glands look like they're still glands, or do they look like they're having a party that kind of a rage? And at a certain point, the doctor may say, all right, well, this is, let's say it's a carcinoma. Let's say it's breast tissue. Well, I also want to see some other aspects about this. I want to see, if you would, what type of things, chemicals are being expressed by this tissue. And we'll do immunohistochemistry stains. So in breast cancer, we might be looking at estrogen reception, progesterone receptors, and HER2/neu, as well as Ki67, which is a measure of mitotic rates. On some levels, we might even get in, depending on the case, we might even get into this molecular component. It could be FISH, so fluorescent in situ hybridization. That's often done as a reflex to HER2/neu. And ultimately, the physician creates this report, and the final report's issued. That's the process. But during every part of this process, pieces of information are being gathered and recorded. And at the very end, we do a synoptic report. And this is a slide I changed because cardinality within PowerPoint really stinks. But basically, what's important here is just to know some structure. every patient has a case. All right, patient has a case. Every case has one to many parts. So depending how the surgeon removes and provides the tissue, the gross tissue specimens to the techs and the pathologist, we may have one or many. We may have on very complex cases, we may have 20 parts. Each part will have one gross description. So this describes the tissue, what it looks like and how big it is, how heavy it is, at what time did they put it into formalin. But then every part will get cut, right? We'll get a tissue paraffin block made, and we'll have several slices depending, and there's protocols depending on the type of tissue and cancers we're considering that are made. And then there's a microscopic examination that's done. And then in some cases, special studies. All of that information is consolidated into a final report. And this is going to be important to remember in a minute. But the final report in synoptic style looks something like this. On the left-hand side, you see all of the categories or pieces of information about the tumor that the pathologist needed to assess and communicate to the surgeon, to the oncologist, and anybody else in the care process. The synoptic report is considered the minimum required data set for reporting a malignancy by a pathologist to a consumer of that data. In the United States, it's a required structure to use a synoptic style, or make sure that your synoptic data elements are present. And it's required for all cancer resections, not necessarily for biopsies, but for resections. And it does sometimes include, as it does here in the bottom, some ancillary testing. In this case, it's mismatch repair by immunochemistry. So that's kind of the world of pathology. So our job over the last several years was to develop all the SNOMED content necessary to unambiguously represent all of the data set or cancer protocols as published by the body pathology. And, that would be the College of American Pathologists in North America, the Royal Colleges in the broader United Kingdom, right? The ICCR, which is the International Collaboration on Cancer Reporting, which covers basically all of Europe and Australasia. The reason, the concepts had to unambiguously and do have to unambiguously represent each data element after it's been recorded and then stored in the database. The reason for that is in 2005 and 2009, the CDC studied what the College of American what content had SNOMED had and how it reflected data as published by the College of American Pathologists. And they said it's insufficient, it's not useful, and so don't use SNOMED until SNOMED gets fixed. But we want SNOMED. That's what they said. So that's the gap we sought to fill. So it covers multiple protocols, fills a big gap. And yeah, I'm gonna move on. All right, just so you know, it's all done. Well over 1,000 concepts, 100% of CAPS solid tumors for both adult and pediatric tumors are done. The College of American Pathologists right now is just validating the set. So this will be distributed throughout North America. So this is how data is going to start to be coming at us in our electronic health records. There's a conversion thing called a C-key. Well, that's beyond the scope of this. And most of ICCR is done. We intend to have SDC fire questionnaires published by this group and available on the Confluence site here in the next 6 months. So the synoptic structure is important to understand. Everything is a question and an answer. So everything is a dyad, if you would, or a tuple of two. It's an observable entity with the corresponding observation. Yep. So what's that? Or value, yeah. So the thing that we want to make sure is that the question describes, this is what I'm reporting, and this is what I saw, right? So I'm talking about tumor invasion. Here's what I saw where it invades to, right? So but the question carries 100% of the context, context. That's important to understand. And I think that's the biggest one on that one. These are all the content areas that were represented. So that's important to know. And I'll get to that in a minute. So some design assumptions. So things that people need to understand when they're looking at the data. We do use observable entity hierarchy. I'll show you the components we use in a little bit. The question has to contain all the context to unambiguously interpret the observation. So we'll talk about that in a moment. Explicit pathology knowledge is not carried by SNOMED. That's important to enumerate. So for example, if the pathologist says it is a mucinous adenocarcinoma, you need to know where it came from. So if I'm talking about the histology type of a colon neoplasm and it's mucinous, versus that, a breast observable histology type of breast tumor and it's mucinous. There's a difference. Mucinous tumors are mucinous tumors, but the amount of mucin it takes to qualify the break point between a mucinous and a non-mucinous tumor in the breast and the colon, that's pathology knowledge, and there's a different break point. We don't intend or pretend to convey that knowledge. That if the physician says it was a mucinous adenocarcinoma, it was a mucinous adenocarcinoma, and they express their knowledge. So that was always a bone of contention with the pathologist. Sometimes they want to overload or wanted to put too much pathology knowledge there. Anyway, so ultimately what happens? Every data element, in this case, an ICCR data element, on the right-hand side, it's a requested observation. What's the histology type of the colon tumor? Well, there's a series of controlled values that exist in the colon. You can't have certain types of cancers that in the colon. Those are on the list. And here's the SNOMED CT bindings. Just one example. And if it were a serrated adenocarcinoma, there you go. We have histology type, primary malignant neoplasm in cecum and/or colon and/or rectum. In other words, the colorectum is a serrated adenocarcinoma. So there's your question answer pair. Okay. And all right. You talked about the information model as it relates to clinical findings or medicinals or laboratory. These are the attributes we used extensively in the observable for cancer pathology. We talk a lot about property. So target values here really talk about length, how big the tumor was. Presence is a particular thing there or not. Subtypes of histologic features, so grade, histologic type, histologic architectural structure, location, anatomic location. The property inheres in, this is always the mind bender. So the property that we're measuring, let's say it's histology type, well, it exists in something. Well, it exists in a neoplasm or a malignant neoplasm. So we always have an inheres in, and then we have this thing called an inherent location, like where is that neoplasm in the body? Oh, the neoplasm's in the colon. So it's almost like it's a triplet. And when we do this, we use component oftentimes relative to direct site, scale type characterizes and process extends to. These are important. I bring this up because when you use ECL, you need to know what the concept model says about your domain. So if you want where to find the context or much of the content in the browser, if you looked at proliferative mass observable, you can feel free to pull it up. You'll see a whole bunch of stuff. Also under tissue specimen observable. Just a couple concepts. There's a lot of legacy content there that we are getting ready to inactivate because it's not defined. So if it is fully defined in these hierarchies, more than likely it's new content or edited content. If it's not fully defined, it's likely legacy content and will be inactivated over the next several months. answer content is always found in the hierarchies that are consistent with the property target. So if you're looking for, if you're measuring presence of something, presence, absence. If you're looking for histologic type, you're going to go find things in abnormal or morphologic abnormalities. If it's talking about an anatomic structure, like where did the tumor grow to, you'd be looking at anatomic structures. Okay. We did the terminology findings, don't we do that? All right, a couple things we need to know when we're storing these things. We do have to maintain that question answer pairing. Okay, so that's important to understand. So when these data come across and you're storing these data in your, whether it's in your electronic health record or it is in your analytics platform, it's important to know that you maintain that question answer pair. You do want to, if possible, maintain, in essence, a cancer pathology report is very similar to a blood panel. You order a CVC and you're going to get about 20 different results, or I don't know how many it is, Stan, but in essence, a synoptic report is similar. In one sense, you want to keep them bundled, or at least know that they came together, but you can analyze each and every one of them individually. And so it is important to know, though, that the question answer pairs have to be together. Okay. All right. And that's actually kind of what I wanted to show here. This is you were just asking, Rachel, what are we doing? Well, this is how we store our tumor data in Nebraska. Basically, you have a case, and gosh, I feel like I need to get over there and point. We have a case. A patient, belongs to a case belongs to a patient, and a case has a case part, and the case has a synoptic report, and the synoptic report has observations. On the left-hand side of the graph is all relational database management. It's really easy. I mean, that part. When it comes to SNOMED, because SNOMED's complex, we store all of our SNOMED content in a graph data set that's with a graph database representation of Microsoft SQL Server in the same data set, so that we can leverage in a runtime environment the same things we're trying to do here with ECL. But in this case, we can execute that same query. And instead of just returning concepts, we can return the SNOMED concepts. Actually, we save those SNOMED concepts, and then we return the actual facts or the findings that are stored about patients, as opposed to just all of our SNOMED data. So you actually get the data right back. Okay, so in the graph databases in ECL, it's a knowledge graph. All right, so why do we care? So here's if we wanted to do some fun queries, and Jim, how do I get to, yeah.
Can I make a comment?
You can.
I think that
You better hit your thingy, because otherwise you'll be in trouble. Eventually we learn. It's why we evolved, but not much. It's on.
What Scott didn't mention, or at least I didn't hear, is that this data, which previously existed only in text reports, okay, basically across the world, is now available and computable, okay? And it's important data from the standpoint of staging the tumor, knowing something about its behavior. And so frequent questions come from the research community and the clinical community about the nature of the cancer. And what Scott is going to show you is retrieving discrete facts about those cancer cases.
So, because how many of us have been asked to find patients with these characteristics and these characteristics about their tumor for potential participation in a clinical trial? Those are types of things we get on a regular basis. Or I want to look at survivability over time based on these other phenotypic expressions of our patients. So we have some time, right, Jim? Jim?
What?
We have time, right?
You have another 20 minutes.
Oh, for goodness sakes. Where is your browser? Excellent. So, let's see how quickly this does. So proliferative mass. Since we've got a minute. Okay. So subtypes of proliferative mass, if you would, this is the entry point into much of the observable entity content, particularly histologic features of the of tumors. So the content is relatively tight, with the exception of the ancient content. But we get into all sorts of subtypes here. So what I do want to show you is, I'll give you an example of how in depth this was. So histologic type colon. All right. Just because it's important to understand. So when we look at how this content was built. Okay. I have to point. Sorry, I'm just a pointer. What's important to understand is, so this is histologic type of primary malignant neoplasm of the colon. In this case, the colon, not the colorectum. The property we're using is a histologic type. Okay, that was a property concept we had to make because it didn't exist. So how do you measure something that you can't define? Well, you create a definition, I suppose. In this case, that was important. In this case, here's in a malignant neoplasm. That's important. This is this histology is going to exist in a neoplasm, a malignant neoplasm. It just so happens that malignant neoplasm is in the colon. And it's important because just because you have a malignant neoplasm in the colon doesn't mean it's a colon neoplasm. It has to be a primary colonic neoplasm. And that's where we have this thing called characterizes, and it says characterizes malignant proliferation of a primary tumor. So in essence, this is a primary colorectal cancer. Okay. Then you'll see some things that are very consistent with the observable entities and things that we've seen in the Loink ontology. We have a technique. In this case, we're using an anatomic pathology technique. Time aspects. These are all single point in time. We're not measuring anything extensively. The metabolic process is stopped. This is a one-time measurement. And in this case, it's a nominal value because we're just going to return, we're going to expect somebody to give us a string. It's a carcinoma, it's a signet ring cell carcinoma, it's something like that. But it's important to understand that indeed, those are the attributes that we're going to use and use pretty significantly. The classification's nice because this now classifies as it's a histologic type of a malignant neoplasm, and it's also a histologic type of a primary malignant neoplasm. So in this case, which is about 95% of the time, the pathologist knows the primary. They can differentiate that. A couple other things that are important you might want to know, and you can do this all the time. Invasion is an interesting thing. So anatomic location directly invaded by. So, and Stan, this is part of the things we were talking about a little bit yesterday. So in the world of cancer, we want to represent, there's stuff that's going on. The observation is about something that's going on. So this is when we talk about invasion, what we're saying is, okay, what are we measuring? And in this case, we're measuring anatomic location. Invasion is represented in two different ways by the pathologist. In certain organs, they say, hey, the tumor starts here and it grows through layers of tissue. And so they're just telling you, tell me where it stopped growing. And in some pieces of or parts of our body, it's not, they're not layers, they're just things. So the prostate is one of those. The lung is one of those, where you basically say, well, did it grow here? Did it grow here? Did it grow here? So we talk about presence. So is the tumor present in these locations? But basically what we're saying is we're looking at the key feature here is we use characterizes twice. One is characterizes as malignant, it's primary, and the other one is direct local invasion. So we're characterizing this process called direct local invasion. So when I'm looking at something on the slide and it's a colon tumor and it's in the colonic muscularis propria, right? It's important that we say, well, that's where it's grown to. It's not where I found it. I can have a trail of breadcrumbs that goes from the origin site to that layer of tissue. And the pathologist will make the determination what that means. Growth is bad, that I can tell you. So that all being said, those are just some examples of what those look like. But now if you wanted to do an ECL query, and then we do that, this would be something we can go we can use the ECL, we can use the builder. And a lot of times what some of the questions are, right? So I want to look at, let's say, histologic grade. Right, so I want to find all descendants of histologic grade. And just to show you, there's lots of ways to measure grade of histologic grade of a neoplasm. Some have techniques associated with them, others don't. So that would be for any organ in the human body that we actually measure histologic grade on. But what I really would rather refine that. So maybe I want to say histologic grade. And what's neat about this is you can do this in a couple different ways. You can keep adding constraints, or if you know your hierarchy, you can do it in the target value. So I could say histologic grade of colon. It's going to bring it up for. Sometimes it's nice to shortcut these things if you can. How about that? We'll just say. We'll do it that way anyway. Sorry. Just for fun. What's kind of nice about ECL is you can just play around with it. I'm going to just do histologic grade and I'll just refine it for grins and giggles. So I'm going to look at histologic grade of the neoplasm and I'm going to add a constraint. I might say and inherent location and self. Jim, where did it go? And self. Oh, did I add it in the wrong spot, Jim?
You did. You're not adding a refinement. You're expanding
No,
definition of the focus.
Oh, there you go. Sorry about that. All right, now I want to look at inherent location. And I might want to say I want to look at the GI tract, gastrointestinal system. So gastrointestinal tract structure. These are always kind of fun. I'll say, okay, so now I'm going to execute that query. And what I find 13 concepts. So histologic grade of all sorts of things, anything that's in the GI, this part of the GI tract. Okay. Now, if I would have said the digestive system, it would have given me everything from, well, in using a little bit of colorful Nebraska language, everything from the asshole to the squeak. So basically from your mouth to the exit, because that's all part of the digestive system. So, but in this case, we said the gastrointestinal tract, so we're confined, and we get 13 concepts. We'll get it, we can refine that more. And I am just going to say, oops. Why don't we say colon? Actually, we say colorectal. Oh, there you go. So we have the structure of the colon and or rectum. That's one of our newer ones. Actually, I think, Jim, when did you, this is an update as of when?
We have the SNOMED International June.
Okay, so this won't have that. All right. Okay, so we'll just do colon. Interestingly enough, part of developing terminology and growing with it is this was fine for the College of American Pathologists when we said colon. And then we went over in the Australian and said, well, we also mean rectum. And we said, oh boy. And the colon and the rectum are not the same. And the colon includes, these cancers include the cecum and the rectum, as well as the colon. And so we had to create a structure, the colorectum, which is the cecum and the colon and rectum, not just the large intestine because it has an appendix. So we execute this, and this is something I wanted to show. So in this case, we have histologic grade of primary malignant neoplasm of the colon, but we have a second type, histologic grade of primary malignant neoplasm using World Health Organization 5th edition technique. This is actually really important when we talk about both temporality, over time, as well as international differences. In the United States, in North America, we are still using a 4-tier grading system for colon tumors, GX through G3. The rest of the world, the World Health Organization has gone to high-low. So, but we're asking the same thing. It's the same subject matter, but the value set's going to be different. And so this is really important and an important distinction. So, and why ECL is really important. When we do these queries, especially when we're looking at international data sets, we don't want to be so precise on our query that we inadvertently leave something out or isolate something. And as Paul and I work on things where we try to look at how the Dutch, for example, versus the Brits versus the CAP, the North Americans measure things. It is actually really important that we do a high level of queries, a histologic type of this organ, and we see that, especially if we're looking at real data or value sets as published by other organizations, we see that, the Dutch don't have anything that's histologic type full stop, but the US sure does. It has, and here's the target values that are typically reported. Well, the Dutch, though, don't ask that, but if we do a query that is logical and brings the logically subsumed concepts, we can see that, they ask the same type of question, but they're using a different method. So, and this actually we're finding to be quite helpful because there's a conversion factor that can be used here. And it's important because we can look at international data sets and harmonize them. At any rate, questions. That was really fast and there's a lot of stuff and it's very, very specialized, but any questions, comments? You want to see the gross pictures again before your beer? No, got grosser ones. Yeah, no. Holiday pictures, yes. Put them on your Christmas cards. Okay, all you, Jim.
Thank you, Scott. We're just about at the end of our time. I guess I should pause and ask if there's any, excuse me. We're just about at the end of our time. I should pause and ask if there's any questions for any of the presenters. I would add to Scott's use cases that, retrieving data on pathologic data on all of my cancer cases is a big deal in clinical cancer research. So unfortunately, it's also complicated, but just as an incentive, if you work in that area, it's worth taking a look at it. In the handout material, I've also included a short presentation on a decision support application that we have actually deployed to a dozen hospitals in Nebraska for an antibiogram-based decision support tool for prescribing empiric medications in patients with infection. And, this is content that Stan wasn't comfortable to dig into, but it's about, what is the bacterium, the bug that is infecting the patient? In our experience, what are the types of antibiotics that are indicate sensitivity to that bug? Again, that's laboratory data. Okay. Then from that, tying the substances to tying the susceptibilities to the RX norm set of those antibiotics that basically are available, okay, is all of the steps, if you will, in building the decision support tool, which we, are providing to our affiliated hospitals. So you can look for the slide set, and that'll also be in the ECL work. I would mention that we are updating the ECL slide based on some new material. So check later today if you plan to go ahead and work on it further.
Yes, because I opened some files, it says invalid, like error.
Says what?
I opened some files from the handouts folder, it says invalid. Maybe.
This is on the GitHub site?
Yeah.
Yeah, okay. We'll check it out right after the, but I can guarantee you that material will be available for an indefinite period. And as I say, the browser that Rory has deployed will be available for a month, but the NE Lexicon site indefinitely. And if anyone has interest in contacting us, drop me an email. And I'll route your question to the individual who is involved and set up the links. Okay. Any other closing comments or concerns or?
Just another question that's a little bit related to what Scott said. So, and it's not for this session, but maybe we asked if also possible that the UCC TNM. We also asked if the UCC TNM could be admitted to the SNOMED, and that would be discussed last Sunday, right? Yeah. Well, what's the update? Oh.
So one thing about cancer pathology,
No, we're hearing you.
you can hear me. The synoptic report is often used to stage a tumor, which is shorthand for prognosis. Tumor staging is how bad it is, right? And it's in the common system used for solid tumors is TNM, tumor node metastasis. And it's frankly, it is shorthand for how bad it is. In the US and North America, the American Joint Committee on Cancer publishes their requirement for TNM staging by tumor type. It's used in North America. It's not used in Europe or anywhere outside of the US. The Union of, Cancer, International Union of Cancer Control. The French always reverse the words, Olivia. I don't know what's up with that. Anyway, they use the TNM as well, but they're sometimes the definition of what a T1 tumor and a T in the colon by UICC or AJC is different. So yes, it's being pursued. It's approved to pursue, and they're ready to help. And AJCC is also helping. So it's just going to be its own taxonomy. It's almost a duplicate, just that will say UICC in the name.
Difference will be more because the ICC is now bringing it out modular for the 9th edition, and the UCC will do it in one. So I think it's very important. It's very important, of course, when you do research on a long stretch, let's say beyond 1 or 2 TNM additions, then it's very important to know that in the meantime, sometimes the definition of a T1A over T1B for something can be different. And if you don't know that, then you can't do good research over a long time period. So for us, it's very important that the UECC TNM was also now admitted, because from the 8th, what Scott already said, from the 8th edition, there are already differences. And I think that will be more in the coming years. So, but this was very thing, because must say that was an exercise from a lot of European countries who wanted this. So we did well.
Thank you for those comments. Is there anything, Chris? I'm sorry, is it Chris? Is there anything we should ask them to do in terms of filling out evaluation of the workshop? I'm not familiar with what SNOMED has set up.
I'll find out. And we can always send something out. We've got a list of people that have been on the.
All right.
Also, the video will be online for a month afterwards as well, on the event lobby. So that's useful to know as well.
Yep. Rachel?
First, well, this has been really great. And I see from a research perspective, the value of this being able to combine these different terminologies, the LOINC, RX norm, and SNOMED into a query for a research population. So if I was describing this, would I say that this part of the phenotype definition, because I'm still imagining some of the temporal stuff would be separate, that would be handled in the database, like visits in the past 12 months, 2 or more of these codes in that time. So I'm imagining that would be separate, and that this piece would be the value sets, the lists for each of these 3 areas. Would I say these are SNOMED intentional definitions? Is that accurate, or would it be ECL queries for?
No, I mean, they reflect, real life experience we've been having in PCORNet. And to go back to the original or my discussion, computable phenotypes really are frequently request information about how were they treated, with what drugs, what was the nature of the case, for example, the stage of the cancer. On the adaptable query, those with renal insufficiency as measured by a random serum creatinine of greater than 1.5, that becomes part of the computable phenotype. So all of these data sets, data types in SNOMED are frequently referenced. Now, what is new, of course, is that, we're talking about actually having all of these together on one computable tool set. All right. Stan, do you want to make any further comment on that?
No, I mean, I don't know that I have anything. I just second that. That's exactly what we're trying to do is, I guess I could say a little more. I mean, there are all kinds of things that we want to do and we haven't been able to do with LOINC. So, from LOINC, if you're talking about antigens and antibodies of microorganisms and things, then you can find that. But if you want to know something about the relationship of this bacteria to, other bacteria that are in the same class or the same, that's not part of LOINC, but it is part of SNOMED. So you can basically, any part of the LOINC code now, you can look at the relationships and use those relationships to further classify and, discriminate the data that you're working with. That's the real power, that we're trying to.
Well, and to elaborate on one of Stan's use cases, if you're a public health official looking for a definition of influenza-like cases, for the fall season, and you basically want to be running queries on all of the lab tests that may have identified in all of your organizations or any of your organizations that the patient had influenza. gathering that that set of appropriate test codes can be done, but it's laborious and it is error prone. Am I fair in that in, Stan?
Yeah.
So,
So again, so if I was describing, maybe I need to refresh myself on your first slide. Are these ECL definitions, I guess, or is this the ontology? I mean, this is beyond SNOMED?
well, I think it is, you know, we have new opportunities that SNOMED in the snowstorm terminology server is creating tooling that can take advantage of the increasingly extensive knowledge base in SNOMED, LOINC, RX norm, and basically mine that as a part of our our data use process for whatever use case, public health, research, et cetera.
Yeah, thanks.
Any other closing comments, Charles? Okay. All right. Well, thank you all for coming and actually persisting till the end of the day.